All right, let's talk about storing and organizing data here next. If we dive into this particular module, we're going to discuss a few things. We're going to talk about storage types that are found in modern data architecture. We're also going to talk about different storage types, also options to match the storage for your needs, and how to secure storage practices for cloud systems. These include things like modern data architecture, data lake storage, data warehouse storage, purpose-built databases, storage in support of a pipeline, and securing storage. All right, let's go ahead and first talk about storage in the modern data architecture here. A interesting way to think about this is that storage is an iterative data pipeline, and it's not a linear process. So the data is ingested into a pipeline and is placed in the storage, and as a result of that, the data can be removed, it can be processed, it can be returned, and this in and out cycle of data illustrates why a pipeline is really the best way to think about it. And so if you think about this, it means that the AWS Cloud simple storage like S3 will provide the object storage that's the center of that pipeline, and Redshift would provide things like the data warehouse, and the service would then store the structured and semi-structured data from relational databases like Amazon Aurora and non-relational databases like Amazon DynamoDB, and even things like graph databases. And the type and volume of the data is growing really at an unprecedented pace, right? So we see that there's large language models, there's data science, there's business analytics. All of these things are driving the storage, and a modern data architecture will give you the best of both a data lake and a purpose-built data store, and it gives you a low-cost solution using open standards as well. And so a modern data architecture as well isn't going to have a data silo, although it could have one, but it will enable people to do lots of different workloads like analytics, ML workloads, etc. Now, some of the things that are important to define here are the key terms. Block storage is a dedicated low latency storage for a host, and block storage is dedicated to an instance and behaves like a direct attached storage solution, like let's say a physical hard drive or a storage area network. File storage stores data in the form of a file, and this means like a highly scalable storage that's managed for you. And this could be related to, let's say, network attached storage. And then object storage is used to do things for unstructured, semi-structured, and structured data. Now, the AWS solution is called S3, and we'll talk about that a little bit more. The interesting thing about S3 is that it's highly scalable and effectively infinite capacity, in terms of the real world usage. And data in a cloud object storage is handled as an object, and then each object is going to be assigned a key, which is the unique identifier, and the key is paired with metadata that's attached to an object. And these AWS services can use that information to unlock a bunch of different capabilities. And due to the economies of scale, this cloud object storage comes at a very low price versus traditional storage. So if we think about what this means, is that there's a catalog layer in the storage, and this includes things like business and technical metadata about data sets. The metadata can support things like the ability to find and query data that's stored in the data lake or data warehouse. And in this architecture, this would be called AWS Lake Formation and AWS Glue working together. And this would provide the ability to both collect and store the metadata so that you can access it. And the catalog is useful because it makes it easy for consumers to actually search and explore the available data. Like, it's one thing to have a bunch of data somewhere, but if you don't know what's in there, you have a swamp, basically, not a catalog. And that's why it's so important to have metadata. And the Amazon S3 system is going to provide object storage for structured and unstructured data. And it's the foundation of data lake architecture. And you can easily store and access and query data from many different data sources. And then you can use the data immediately and place it in a low-cost, long-term solution like Amazon S3 Glacier, for example. And with scalable, flexible, and durable storage from S3, you can get this concept of, the 5 Vs like velocity, volume, etc. Now, Amazon Redshift is a data warehouse that uses SQL to analyze both the structured and semi-structured data across a warehouse, operational database, data lake. And this service is what AWS uses to deliver the best price performance at any scale. And because the service is integrated with other services, including database and ML services, it can help you handle complex analytics workflows. So there's some interesting things about Redshift here that I've experienced in the real world, in that a lot of times it's easy to think you won't need basically like a big locomotive, right, to move things around. But one of the problems with undersizing things when you're working to build a SQL-based solution at scale is that later you could have performance issues. So one of the things that's nice about Redshift is if you do conform to some of the design characteristics of a Redshift system, you can get effectively infinite scale, which at a later phase of a company could really come in handy as you start to do analytics. I've personally experienced, trying out Redshift. Oh, maybe I don't like these characteristics of it, but then later, 3 years later, I regretted not using it and being talked out of it because of the fact that it can scale no matter how big of a load you throw at it. Now, if we look at the comparison between a data lake and a data warehouse, it's important to think about the concept of complementary storage types, and a data warehouse is going to get a lot of the data from the vast repository that's found in a data lake. And the key differences are in the data quality characteristics. So a data warehouse is going to store highly curated data, and the data that lives in a data lake, though, can be raw, it can be untransformed, and it can be uncurated. So it's really like a raw asset that may or may not add value, where a data lake has a little bit more granularity to it, a little more usefulness in that you know what's inside of there. Now, if we think about the availability of data lakes, they can store both the relational data and data from a line of business and non-relational data, and this could include things like mobile apps, IoT, social media. And you could just put things in there and you don't have to necessarily focus on a design or usage in the short term. And the schema doesn't have to be defined either. And the data lake in AWS is going to give you the ability to essentially scale and also have durability. And then you can employ other services like ML or maybe third-party analytics to process that data. And you can also use things like Amazon Athena and Amazon EMR to do things like AI and ML, and even transform and query the data in place. So a service like Athena, for example, is a pretty good example of processing the data in place, in that you're able to actually do a query because you have the metadata, and then you can actually just selectively access the parts of your data lake that you need, but you can do it from an intuitive way using SQL. If we think about S3 storage classes, this is another must-have to consider when you're building things for AWS, and that you can figure out what is the optimal purpose of the storage that you need. And Amazon provides really a pattern for the migration of on-premise analytics, and does things like read after write or list consistency. And this capability removes a lot of the changes that are necessary if you're going to migrate out of a physical data center. And some of the things that you can consider as well are that, you can have an S3 bucket configuration that's eventually consistent. This also means if you delete a bucket and then immediately list all of your buckets, the deleted bucket might still appear in your list. So there's some nuances to it, but it's a very flexible system. There also is a multi-part upload in terms of AWS S3, and this lets you upload huge, large objects. Let's say you're working with, computer vision, and when you start a multi-part upload, the S3 will automatically divide this into parts, and they can be uploaded independently and in any order. And a transmission failure is going to occur, for example, during the upload, and this could, cause other issues down the chain. So a few different things to think about are that, with multi-part uploads, you can utilize an MD5 checksum to verify the data integrity, and you can specify additional checksums if they're required. And then these checksums are going to be performed on the individual objects rather than the entire object. So yeah, there's nothing more frustrating than trying to synchronize a huge file and it fails partway through, and then you have to keep restarting it. And that's one of the advantages of doing a multi-part upload. Now, if we think about storage classes, one service to consider is S3 intelligent tiering, which is pretty smart because what you do is you do automatic cost savings for data with unknown or changing access patterns. And then S3 will be the standard for frequently accessed data. So essentially there's some intelligence here where you just click a button and you say, look, save me money, and it does a pretty good job. Now, if we think about other services here in a data lake, another thing to consider would be, Cognito or API Gateway or Lambda, AWS Glue or CloudWatch, DynamoDB, etc. So there's a lot of services that can be involved with a data lake. Now, let's think about how this would work. With lake formation, you can identify existing relational and non-relational databases, or even just raw S3, and then you can import them. And then you can use the lake formation to crawl and read the data sources so you can create a data catalog. And then you label that data inside. And this allows the users to find things in an efficient manner. So really, if you think about it, basically doing a linear search through something or just crawling through data every time you want to do a search is very inefficient. I mean, you can test this out yourself, do the find command on your computer. And if you have a multi-terabyte hard drive, it's going to take a long time to find something versus use a system that uses metadata, like, for example, Spotlight on AWS, where you're actually querying the metadata versus actually crawling the file system. So really, this has been around for quite some time, but at scale, it really starts to become an issue. And this is why you want to have a catalog for your data. Also, governed tables are metadata tables that are unique to lake formation. And these allow you to do things like make sure that there's atomic, consistent, isolated, and durable transactions. And you can also, look at the different queries that users are running. And data governance is going to be a big issue, I think, as we get further and further into AI. So Amazon S3 promotes data integrity through strong data consistency and multi-part uploads. And these features enable that data to be retrieved from storage that isn't partial or corrupted, and that large files can be uploaded in parts without corruption. And this lake formation allows you to use these governed tables to enable concurrent data inserts and edits. And this also allows users to update data sets while others are simultaneously running queries or doing ML models. Okay, let's talk about data warehouse storage next here. These are centralized data repositories, and the data is contained within the warehouse in a form that can be processed and analyzed so you can make decisions on it. So this is effectively data science. And you have structured and semi-structured data from sources like transactional systems and relational databases. And the data warehouse consists of 3 tiers. At the top is a front-end client, which represents the results through reporting, analysis, and data mining. The middle is made up of an analytics engine, which is used to access and analyze the data. And the third tier consists of the database server, where the data is loaded and stored. And this data is stored in a couple different ways. One, fast storage, like SSD drive. Another one would be infrequently accessed. So this would be data that can be automatically shifted between 2 storage types based on how frequently it's accessed. And a data warehouse can contain multiple databases as well. And these could be structured or semi-structured. And when the data is ingested into the warehouse, it can be stored in tables. And these can be organized inside of schemas. If we think about Amazon Redshift, it has multiple node types you can choose from, and you can select the best node for your requirement, like dense compute, for example, could be one, or you could use RA3 nodes to optimize the data warehouse by scaling and paying for compute and managing the storage independently. If you're using the dense storage or DS2 nodes, you can create a large data warehouse by using low-cost disks as well. Amazon generally recommends you upgrade the DS2 to RA3 nodes to get more storage and performance, but the DS2 nodes are often used when the amount of data in the workload exceeds 500 gigabytes. Another thing to consider would be that A leader node would coordinate these compute nodes within the cluster and communicate with the client application. And with certain SQL queries, the current schema function can only be run on the leader node. So that's one of the capabilities of this warehouse system, is that you can also query basically the compute node, and an error will indicate that the function is supported or if it's not supported. And this leader node is responsible for compiling code for the elements of the execution plan. And then the compute node is actually responsible for running the job. So there's some scheduling here that occurs with this data warehouse. With the Redshift Spectrum, you can write SQL queries that combine the data from the data lake and the data warehouse. And so when the user makes a query, that could include the data from the data lake, and then the Redshift Spectrum will get that schema information, right? Because we already have the catalog, and then it can query it as well. So in a nutshell, data warehouses are a centralized repository that consists of 3 tiers and can store structured data. The data is ingested into a data warehouse, and it's organized into tables and columns. And Redshift is a fully managed data warehouse that's provided by Amazon. Okay, let's talk about this concept of a purpose-built database as well. What's interesting about this is that I think in the old days we used to only think about SQL, but it's important to consider the workload of the application. Is your database going to use e-commerce or content management or analytics, right? And as you start to dig into this, it's going to give you more of an idea of the options that you have. Let's go ahead and define a few things here. So first up, we have transactional. So a transactional workload is characterized by a high number of concurrent operations, where each operation would be a read or write. And most user-facing applications would include things like e-commerce, mobile gaming, social networking. Analytical workloads would do aggregation. They would summarize large volumes of data. And you could think of this as an OLAP workload. There's also caching. So in a caching workload, you would compute and store the frequently accessed data in a separate database for faster access. So a good example would be, let's say, a recommendation engine, right? That's very computationally expensive. You could store all the recommendations constantly in a cache, and then you would easily be able to provide those recommendations. Now let's take a look at the old model, which is a relational database. That's probably the most traditional model. And these are used in things like enterprise resource planning, customer relationship management, and e-commerce. In terms of high traffic web applications, gaming applications, key value is starting to become more of a common database. And DynamoDB would be a good example of this. And it's a fully managed non-relational database that provides fast, consistent performance at any scale. For content management, catalogs, user profile, Amazon Document DB is also a system that can be used for graph databases, which are becoming more and more important. You would use Amazon Neptune, and this could do things like fraud or social network analytics, knowledge graphs. Personally, I think graph databases are pretty interesting because you can actually do different kinds of descriptive statistics, like, for example, centrality or PageRank. Like, you can look at things using a graph technology, and so the descriptive statistics are not the same as you would have in a maybe traditional data science workflow, and that some of these other metrics can become very important, like where's the center of this graph relationship? Who's actually connecting to who? And when you're using AWS purpose-built databases, most of the operations burden is handled for you. So let's take a look here at what we covered. And really, we talked about application workload and access patterns. We talked about how these actually come into play when you're choosing your database. And there are more options than just a relational database. And they could include even a graph database or a key value database. All right, let's talk about supporting a ETL and ELT pipeline. So a structured format is going to be used for analytics applications like Glue, Spark, or EMR, and this transformed data is loaded into structured storage like a data warehouse. But what we're seeing is also a trend towards bulk collection of unstructured and semi-structured data, and it's shifting from just the traditional ETL to ELT. And this data is extracted from the source and cleaned just enough to be stored in object storage like the data lake. Then whatever data transformation engine is built into the data warehouse, this would then access that. And this is a powerful pattern because it uses highly optimized and scalable data storage and the compute power of MPP. So you get this automatic ability by putting this intermediate asset into S3, in that you get effectively infinite compute and storage. So if we take a look at Kinesis data firehose stream, you can do data transformation with data that's, let's say, designed for a Redshift cluster. And this Kinesis data firehose is an ETL service that captures, it transforms, it delivers streaming data to data lakes. And when that data transformation mode is enabled, like the Kinesis data firehose, and it's buffered, this is when you can invoke, let's say, a Lambda function, which would then transform that data and send it back to Kinesis data firehose. And that transformed data must contain the record ID, the result, the data parameters, so that you can actually return that back to the Kinesis data firehose. Otherwise, the records are going to be treated as data transformation failures, and they can be sent to, let's say, the optional backup S3. Now, if we think about a generalized ELT architecture that conforms with storage principles of a modern data architecture, the data storage is ingested and immediately sent to an Amazon S3 landing zone with a data lake. The data is cleaned, it's validated, and then it's transferred within the data lake to a raw zone, and the data is further processed and loaded, transformed, and moved into appropriate S3 storage until it's ready for data warehouse. The ELT pipeline is going to simplify the architecture. The burden of the transformation is then going to be placed on the target system, and this means that the data isn't processed by using intern transformation and buffered memory. Instead, there's dedicated compute resource that's going to process the data, and it's going to greatly improve the performance in the pipeline. So if we think about how storage plays an integral part in ELT and ETL pipelines, the data is going to move in and out of storage numerous times based on the pipeline type and the workload type. And ETL pipelines will transform the data in buffer memory prior to loading into a data lake or data warehouse. And the ELT pipelines will extract and load the data into a data lake or data warehouse without transformation. So the transformation of the data is part of the target system's workload. Let's talk about securing storage, which is a huge topic and very important, and not really getting the consideration that it needs. If we think about storing large quantities of data in a centralized repository, all of a sudden now we have security as a key element of the planning. It's a little bit like putting the gold into a vault, right? Well, now all the gold's in the vault, so we have to protect the vault. With Amazon S3, there's several security features that are intrinsic to the service. So first, let's talk about the durability. And this could be enabled to protect you against malicious deletion and corruption. So that's a big issue. Access policy as well is an important one. You don't want people to have access to protected data. We also have bucket policies and access control lists, or ACLs. These are resource-based policies. And with resource-based policies, this is an excellent way to secure a resource. And AWS recommends using user policies for most data lake environments. You also can do encryption keys. So you can encrypt and decrypt the data assets. And this can prevent users from inadvertently accessing the data access. And in S3, you can also use object tags to categorize and manage the assets as well. And you can use CloudTrail to monitor and audit who's been actually accessing the data. So I think this is another critical one, is that if you don't have data auditing, you're really putting yourself at risk, because you need to see who is accessing this data. And that's one of the key takeaways for a data breach, is that the data is being accessed by somebody that shouldn't have access to it. Now, if we think about security for a data warehouse, a few things to consider would be sign-in credentials. So, account permission, access permission to control access to a specific Redshift cluster, cluster security groups. So inbound access to a Redshift cluster, VPC. This would be virtual networking environment. We have cluster encryption. You can encrypt all the data in the user-created tables. We have SSL connections, so encrypting the connection between SQL and cluster. We have load data encryption, which allows you to encrypt the table load when you upload to S3. We have data in transit. So this protects the data from the AWS cloud, and also column level access control. So you can have certain columns actually be granted or revoked based on statements, and then row level security as well. So there's some granular controls here for security. So a few things to take away from this are that S3 is the core. Resource-based and user access policies are highly customizable resources for securing data lake, and data lakes are built on AWS. And finally, Redshift will handle the security of the service and the security of the database as two distinct functions, and this allows you to have greater security of your data. All right, so that's it for this particular lesson, and what we talked about was defining storage types that are found in a modern data architecture. We talked about distinguishing between different storage types. We talked about the storage options that match storage needs, and we also talked about how to implement secure storage practices for cloud